Dear attendees of the 2022 LISA Symposium, I am Matteo Tomasi, a researcher of the University of Trento and the presenting author of the work titled Analysis of the Grabbing, Positioning and Release Mechanism Performance Sensitivity to Alignment. In LISA-Pathfinder and LISA, the test mass has to be grabbed, positioned and released by a dedicated mechanism called GPRM. In this work, we mainly focus on the grabbing phase. It consists in having two plungers, one conical and one pyramidal, as we can see in the figure, in contact with the test mass inside two dedicated indents machined on the test mass Z faces. To release the test mass, two small cylinders named tip will protrude from the plunger head. The tips will contact with the landing areas in the test mass and the plungers will retract while maintaining a constant preload force. In the last step, the tips are quickly and simultaneously retracted, releasing the test mass into free fall. The objective of this work is to study how the plunger's relative misalignments affect the test mass position and attitude after grabbing. To do this, we needed to simulate the grabbing phase and to find a relationship between successful test mass releases and maximum plunger misalignments. A test mass release is successful when the tip is able to reach the landing area, protruding by almost 16 microns.
To iteratively simulate the grabbing, a fully detailed model of the GPRM will require an excessive amount of computational resources. For this reason, a simplified multibody dynamical model is built involving only the feature of interest of the GPRM. The plunger's head and the test mass geometries are imported from the in-flight CAD model. Ideal joints and lump stiffnesses are used to guide the plunger's motions. A force sensor is placed on the plunger back exactly like in reality to stop its motion when the force generated by the test mass plunger interaction reaches 2 newtons.
Without loss of generality, one plunger is kept in its nominal position, while the other is misaligned along x direction to consider a generic relative misalignment. Several simulations are performed varying the misalignment from 0 to 400 microns with a step of 80 microns. For each step, 20 runs are performed, randomizing the test mass initial position and attitude. At the end of each run, the distance between the tip and the landing area is computed for both the plungers. The tip have a spherical head which is conveniently modeled as a sphere in the software as shown in the figure. The simulation procedure is performed with different friction coefficients. This is done because of the uncertainty on the experimentally measured friction coefficient values. The histogram shows that for a static friction coefficient equal to 0.5, the unsafe grabbings are associated only to the pyramidal plunger. Moreover, they appear only at a misalignment greater than 240 microns. Increasing the friction, the plunger will get stuck inside the test mass indent far away from the nominal ending position. This increasing the percentage of unsafe grabbing also at low level of plunger misalignments. We can relate the quality of the grabbing in terms of plunger indent fitting with the test mass rotation along the plunger axis. Considering the in-flight release data in the figure on the left, we can see that all the points lies inside a triangle which wideness depends on the test mass indent geometry. Looking at the figure on the right, in simulation environment, we can note the same effect. Additionally, we can divide the simulations in safe for both the plungers successfully grabbed, unsafe for only one plunger successfully grabbed, and highly unsafe for both the plunger unsuccessfully grabbed. As we can see, the highly unsafe simulations is only one in this case. This suggests that the unsafe conditions can be compensated with an appropriate grabbing policy. The figure shows the simulation results in terms of test mass position and latitude. We can see that the linear degrees of freedom of the test mass in the figure of the left are less scattered with respect to the rotational ones in the figure of the right. Most of the simulated grabbings produced a test mass state non-compliant with the mission requirements, highlighted with black lines. The scattering is strongly related to the plungers being stacked far from the nominal position. It is advisable to modify the release procedure of the test mass, introducing dedicated maneuvers that should unstack the plungers and improve the alignment. Moreover, the trend of the x degrees of freedom shows that starting from a simulation index greater than 80, the test mass position would be out of requirement. This simulation index corresponds to a relative misalignment of 240 microns. Our analysis shows that the friction coefficient between test mass and plunger assumes a key role in the studying of the grabbing. The friction phenomena coupled with the presence of multiple impacts during the plungers enclosing to the test mass makes the analysis strongly nonlinear. The test mass final position is highly sensitive to small variation of its initial position. In the table, we can see that for similar initial conditions, we can have very different final conditions. For these reasons, we suggest to perform a dedicated experimental campaign which aims to study the test mass plunger interaction parameters in view of the forthcoming LISA mission. Thank you for your attention. I wish to all the attendees an exciting symposium.